In this video, I'd like to go over a few examples and a way of thinking about manual IV flow rate calculations so that we build a deeper understanding. We're going to look at some formulas that oftentimes students are required or feel that they're required to memorize, and we're going to tear those apart and think about where the ratios and mathematical calculations in these situations come from and how we can understand them better. On this page, we see at the top a lot of different formulas that are often used when we're thinking about flow rate in terms of drops per minute calculations. I did a quick scan, a quick Google search, and I found a whole bunch. Some of them required students to think about the volume and drop factor over the time in minutes. Others had the volume and drop factor time in hours times 60 minutes. Others seem to take the drop factor and remove it from a single ratio, a single fraction, and break it apart into two. And then others also tended to incorporate the units themselves rather than thinking about what these various pieces, where they're coming from in relation to the problem. Now, you may have seen some of these before. You might recognize them. There may be one that you have memorized or think about when you are doing these calculations. And I assure you, they're all the same. Every single one of them is the same. And rather than memorize all of these, what we're going to do is to think about them all informally. And down below here, I have kind of this informal formula that I think would be more appropriate when we're moving forward with these calculations. A flow rate, when we see the word rate, we often think about a measure over time. So when we think about miles per hour, that is a rate. We think about a flow rate in milliliters per hour, or pounds per second is another one. There's lots of rates that we see on a daily basis. With a manual gravity set, what we need to think about are drops over minutes. So what I can think about as a nurse is if I know the total number of drops that this patient or a individual needs to receive, if I know the total number of drops and I divide that by the total number of minutes for the infusion time, then this ratio, once simplified, will give me a unit rate. It'll give me the total drops per minute. So what we're going to do now is think about how do we calculate the total number of drops? Where's this coming from? And then we're going to put that together with the minutes. And with this informal approach, the total number of drops, the total number of minutes, we can reason our way through an IV calculation for a gravity set. So what do we mean by drop? A drop is just a measure of volume. So it is a measure of volume, just like milliliter or liter or ounces or cups. It's a measure of volume. And we use the symbol, the unit, GTT, to represent drops. So I could, if I wanted to take an IV bag and ask myself how many drops are in this bag, and here we see this 500 ml bag of dextrose with saline. And what's going to happen in a clinical situation is the tubing that is connected to this bag will take every single one of the milliliters that's floating around. So we have milliliters floating around in this bag, individual milliliters, and it's going to break them into drops. That's what we mean by drops. So this right here is one drop, and the size of that drop is going to be determined based on the tubing that we have. So it'll take all of the fluid that is in this bag, and it will break all of these milliliters, all of this fluid, into single drops, which will then infuse into the patient. What we need to think about, remember, is how many total drops are in this bag. So in order to calculate that, we need to know the relationship between a single drop and a single milliliter, and that is going to be determined from the tubing. On this page, we see a few labels at the top. These are giving us the drop factor. The drop factor is just telling us the relationship between drops and milliliters. It tells us, if we were to look at the packaging, with this first one on the left, that we have 10 drops per milliliter. What that means is that 1 milliliter, or each milliliter in this bag, that if we were using this to hook up to a bag, each milliliter will be broken into 10 drops. And we can use the ratio 1 milliliter over 10 drops if we want to talk about the ratio of milliliters to drops, or we could write that as 10 drops per milliliter, depending on what it is we are hoping to do and what we're trying to reason through. So that is what's called the drop factor. We need this information from the tubing to determine how many total drops. So there are various sizes that we could see. We could see a relationship of 10 drops per milliliter or 15 drops per milliliter. So this takes 1 milliliter and breaks a single milliliter into 15 drops. Or we could see what's called a micro drip, which takes 1 milliliter and breaks them into 60 drops. And hopefully what these pictures below are illustrating is that if we have a drop factor of 10 versus 15 or 60, 10 drops are making up 1 milliliter. Those are pretty big drops, comparatively speaking. So down below, if we were to think about each one of these circles as 1 milliliter, every single one of these milliliters in the bag will be broken into drops. With a drop factor of 10 drops per milliliter, that means this single milliliter will be broken into 10 drops. They're pretty big drops. If we think about a drop factor or a calibration, lots of different phrases that we might hear or see, 15 drops, well, that single milliliter is now broken into 15 drops. So the drops have to get smaller, or they will be smaller, than the other factor. And I'm not counting. I hope that's somewhere close, but we're going to have 15. 15 drops for each milliliter. And finally, for the micro drip, what we see with this tubing, with this drop factor, is there are 60. And you can see as we move into a larger drop factor, look how small those drops are, relatively speaking. That means each milliliter is going to be broken into 60 drops. Right? And I'm not going to sit here and draw 60 of them, but what we see here is there will be 60 drops for every single milliliter. This is what we mean by drop factor. You need this information in order to calculate the total number of drops in the bag, because this is the piece that's going to break all of the fluid into drops, depending on the size of the chamber and tubing that we have. Now, how can we use this drop factor and the volume in our bag to calculate the total number of drops? If you reflect back onto the original informal way of thinking about these formulas, what we need to think about is how many drops is this patient going to receive? This is just taking one measure of volume, milliliters, right? This is one measure of volume, specifically a milliliter, and converting it into another measure of volume, which is just drops. So what we want to think about is, what is the relationship? What is the relationship between the milliliters and drops? That has to be given to us and will depend on the size of the chamber and tubing that we're working with. So right now what we are working with in this situation, we are working with an IV bag that has a volume of 500 mLs. If we look at this bag, we see it has a volume of 500 mLs. And what we know is that this volume is going to be broken into individual drops into the chamber and then infused into the patient. The size of those drops is determined by the drop factor. And what I see here on the labeling, on the packaging of my packaging here for the chamber and the tubing, is that each milliliter will be broken into 15 drops. This is telling me that 1 milliliter will be broken into 15 drops. This is the essential ratio for this problem. I know that each milliliter in this bag will be broken into 15 drops. Now, how can we find the total number of drops in this bag? Well, let's start with this ratio. I know there are 15 drops in every single milliliter, and I know that that's going to be proportional to another ratio of drops per ml, but specifically I am talking about a bag of 500 mLs. What I am looking for is this value right here. I want to know if there are 15 drops in each milliliter. Well, what happens if I'm working with 500? Now, depending on how you have solved these ratios before, I know the most common is cross multiply, right? What we can see also is that we're just dealing with an increase from 1 milliliter to 500 milliliters. That's an increase of 500 milliliters. That means our numerator in an equivalent ratio situation needs to increase by that same factor. So what we see is that each 500 mLs, those 500 mLs, times the 15 drops per ml is going to give us 7,500, and this is in drops. There are going to be 7,500 drops in this bag. I hope that makes sense, because what we see, if we think about the milliliters that are floating around, there are 500 of them, and each one is going to be broken into 15 drops, then I know it's just going to be 500 mLs times 15 drops per ml, because there's going to be 15 in each. That gives me 7,500 drops. That's the total number of drops that are in this bag. We're now ready to think through a flow rate problem. We can think through how we can calculate the total number of drops that are in a bag, right? That's the numerator. If we know the total number of drops that need to be infused, we can divide that by the total number of minutes, and that ratio, once simplified, once reduced to a unit ratio or unit rate, will give us our drops per minute rate. So here we are working with a veterinary situation where a dog needs to receive an IV. Dogs also need to receive fluids via gravity set as well. So here we have a bag. This bag is for lactated ringers, and what we need to think about in this situation to calculate a flow rate, and the dog looks like they need to receive this 1,000 mLs over 3 hours and 45 minutes. So I'm going to start there. I know that the volume of the bag, the volume to be infused, is 1,000 mLs. And the infusion time is 3 hours and 45 minutes. So I'm going to start there. 3 hours and 45 minutes. So thinking through a flow rate problem, if I can think about how many total drops, if we go back to our informal way, how many drops is this dog going to receive, and divide that by the time in which this infusion is going to last, then if I can write that ratio, that will give me the flow rate in drops per minute. Now we have the volume, but the volume is in milliliters. What I want to know is, based on the available tubing, how many total drops is that? So what I need to look at is what's available to me. I look at the tubing, I see that the tubing is going to take each milliliter and break them into 10 drops. So I have a drop factor of 10 drops per ml. That's going to take each milliliter, right? We're talking about a ratio of volume to volume. Each milliliter will be broken into 10 drops. So now let's think about the numerator and the denominator. If I think about the total number of drops, I know I have a volume of 1,000 mLs, and each one of those milliliters is going to be broken into 10. So I know if I take 1,000 mLs and I multiply that by 10, because each one is going to be made up of 10 drops, multiplying those will give me the total number of drops. And there are lots of ways that you can reason through that. You can set that up with dimensional analysis. You can set that up with ratios. Lots of ways. But if you think through that, just what a drop factor is, it's the number of drops in each milliliter. So if I have a milliliter, I have 1,000 of them. It's going to be broken into 10. I need to multiply. And what I find is that this volume, there are 10,000 drops in this bag. So once the dog receives this entire bag, there will have been 10,000 drops that are falling and being infused into the dog. Now let's think about the total number of minutes, the total infusion time. So what I need to think about, again, total minutes. Well, I have 3 hours and 45 minutes. I know that there are 60 minutes in each hour. So if I take if I take 3 hours and multiply that by 60, because there are 60 minutes in each hour, I get that's 180 minutes plus the 45 minutes that is also part of the infusion time. I get a total of 225 minutes. I have the two pieces I need. I know there are 10,000 drops that need to be infused. I know this needs to be infused over 225 minutes. I am ready to put these together. I need to take my 10,000 drops, right, and I'm going to divide that by my 225 minutes. This is that informal strategy, that informal formula. This is going to give me my flow rate. If I take these two values and I simplify them, what do we get? In my calculator, I got 44.4 repeating. 44.4 repeating. Now what we're going to have to do is set this with our eyes. We're going to have to calculate the number of drops that are falling. So this is why for drops per minute, and this is the unit on this, the ratio of drops over minute, I round to the nearest whole number because we're going to be setting this with our own eyes in the chamber. So rounding 44.4 repeating to the nearest whole number gives me 44 drops per minute. This is how many drops this dog needs to receive every minute. And if they do, and there'll be a slight rounding error, but if they do, they will have received 10,000 drops over the 225 minutes. This is what we need to be able to think through. What's the total volume in drops? What's the total time in minutes? And if you know those two things, you can find the flow rate. We have one more example here, and I'm going to give you the opportunity to complete this problem. What we have is 500 mLs of normal saline. It also has some dextrose in it, it looks like. It needs to infuse over 6 hours and 30 minutes. What we have to do is use the available tubing, which is the drop factor. We're going to have to get that from the tubing. And we need to calculate how we're going to set this rate. So what is the appropriate flow rate in drops per minute? Again, if you think back to that informal strategy, think about the total number of drops in this bag, divide that by the total number of minutes, and you should have your drop factor. So if you want to pause this video and go ahead and try that, I'm going to give you a second to do that, and when you unpause it, you'll be able to come back and check the answer. Okay, so I need to calculate a flow rate, and I know if I want the flow rate in drops per minute, I want to think about the total number of drops, and divide that by the total number of minutes. So what I see in this problem, there are 500 mLs in this bag. And each one of those mLs is being broken into, it looks like that's 15 drops. There are 15 drops in each milliliter. Using those two pieces of information, I can find the total number of drops. I have 500 mLs. I'm going to multiply by the drop factor, and what that's giving me is the total number of drops in this bag. And what we see is this bag of dextrose and NS has 7,500 drops. That's the total number of drops. Now let's think about the infusion time. There are 6 hours and 30 minutes. And what I need to find, total number of minutes. So I know 6 hours times 60 minutes will give me, that is a total of 360 minutes. Right? And this 60 is the number of minutes per hour. And I know there are also the 30 minutes, so I have to add in the 6 hours and 30 minutes. So I get 390 minutes. This is the total number of minutes in my infusion time. I am now ready to calculate my flow rate. I have 7,500 drops. They need to infuse over 390 minutes. So I set up that ratio. I'm going to put this into my calculator, and I get 19.2307, and that continues. And again, I know when I simplify these two measured values, I know that this is going to be a drop per minute unit, the total number of drops over the total number of minutes. Now I know I need to round this to the nearest whole number because I would have to count those drops. I can only count the nearest single drop, so this would be 19 drops per minute. Hopefully what you've learned in this video is that the various formulas that you're required to memorize or expected or you think you have to memorize are all coming from the same place. Each one of the formulas, if you were to go back to that one of the beginning slides, each one of them in its own way is calculating both of these pieces. It's calculating the total number of drops, it's calculating the total number of minutes, and it's dividing those two values to find a drop per minute rate. What you need to think through is what is the volume, specifically what's the volume with drops. So I need to think about what's happening clinically in this situation. The volume is being broken into drops based on the tubing that is available to me. And if I can find that volume in the drops based on the size of the tubing, I can divide that by the infusion time. This is a much more robust way of thinking about flow rates rather than pure memorization of formulas.